I'm going to talk about a variety of topics that I've been working on over the last 25 years and kind of give you some reflection on my thoughts on some of the challenges confronting management of the Mississippi from a fluvial geomorphic perspective. I've been working on the Mississippi since the mid-90s for my PhD, where I did it at Louisiana State University and really got introduced to it there. And it's, you know, it's like a fungus or something that just stays with you. I can't get rid of it, even though I go work in other places as well. I love it. The talk is probably going to be all downhill from here because this is the most beautiful slide I can show you. But also this is one of my field sites here along the lower Mississippi, just above the apex of the Delta. And this is in St. Catherine's Creek National Wildlife Refuge. Pointer. Yeah, so it's not, it's pretty well known that the Mississippi has lots of challenges facing it. And these are challenges that are really human imposed. A lot of these are from hydraulic engineering, which has maybe gone a little bit wrong or not as intended and introduced other problems subsequently decades later. I'm not going to go over all of those in detail. However, I firmly believe that in order to understand the problems that you have now and to come up with effective solutions for the future, you got to know where you've been. So you got to know the historical context of that. This is the main area where we'll be talking about today here, really the apex, just above the apex of the Delta. I like working here because nobody else is, for the most part. Everybody's working down in the Delta. You know, this is what you see in the world news so much here because some of the problem, that's where all the money is. But there's a lot of really interesting questions in the alluvial valley, which is, you know, some 1,000 kilometers long here, and hardly any fluvial geomorphologists working up there. You can see the study area here in the Mississippi, of course. I'll give you just a few names because you'll see those on slides or something. Cairo, Illinois, at the top of the lower Mississippi, where the Ohio River joins the middle Mississippi. Memphis, Tennessee. And notice that the river is really against the valley wall for most of the way here, except where it comes out here and flows a little bit westerly. Then it rejoins the valley wall at Vicksburg, Mississippi, and then flows along that, you know, kind of meandering along there all the way down to Red River Landing, which is where we get the proper delta and the Atchafalaya branching off at the Old River control structure. So Red River Landing is really important here. And then eventually we get down to New Orleans there as well. So I'm really working here kind of between Vicksburg, Natchez, and Red River Landing primarily. And one of the reasons for that is because there's no levee against the river there. And so we have kind of a free-flowing river in terms of its flooding and so forth. It's one of the few opportunities that you can really get out and look at these kind of processes there. The other thing is, since I've left the US like 12 years ago and moved to, left Texas and moved to the Netherlands, it's actually not that difficult for me to fly back to New Orleans, rent a car, and pop up to my field area and meet my collaborators and get into some real interesting research there. So that's worked out pretty well for me, even though I'm living abroad now, as I say. A lot of times when we're talking about managing rivers, the big hinge points come with big disasters, and those disasters are usually big flood events. Could be droughts too, but especially big flood events. And the signature one on the Mississippi was in 1927, still the worst flood in US history. And it really changed the whole paradigm of how the federal government dealt with flooding and the Mississippi. And it really introduced a very top-down, heavy federal role in managing the river and introduced a lot of structural engineering. And right after the 27 flood, then we had this national federal act, the 1928 Mississippi River and Tributaries Act, which, by the way, has not yet been completed. I like looking at these dates in the gray literature about this, and they always talk about, you know, completion dates, you know, 1995, 2000, 2005. Now it's in the 220s or something like that. I compare that to where I live now in the Netherlands, you know, and they finished Room for the River. under budget, under time, et cetera, et cetera. So this was really interesting, actually. Anyway, I just want to point out here that it introduced several kinds of structural engineering, or made it much more robust, I should say. Didn't really introduce it here, but that is, we built a whole bunch of dams in the tributaries that are trapping the sediment, causing a lot of problems. We have a big sediment issue here. Channel stable improvement and stabilization. I love that term, improvement. That's what the engineers use. Improvement, we're going to improve the river. No, I don't think so. You're not improving it. You're actually degrading it, especially by doing these cutoffs here. Of course, levees and flood walls, and of course, and we also have flood bypasses here. We have Bonnie Carey spillway just a little bit upstream of New Orleans. This is prevent New Orleans from flooding. It was completed in 1931. It's about 10 kilometers upstream of New Orleans there. If we look at some of this in terms of its impact here, we can see that the cutoffs here, and here we're seeing the 1880 and the 1911 old river courses there overlapped, and you can see what they did is they went and cut that off. Well, the typical response there is we get a nick point, a very sharp, abrupt nick point that is an overly steepened portion of the channel bed slope. And what happens is that starts to migrate upstream and introduces other forms of degradation to the river that were not initially planned or thought about when they came up with the idea to do this. Other forms of hard structural engineering, you're familiar with them, I'm sure. Dikes, these are sometimes called groins in some places. They extend tangent to the riverbank there, and they are trapping sediment in there. And we'll look at what they're doing here. So they trap sediment and they force the current into a smaller channel, and of course create flush out the sediment a little bit. It's better for navigation, and it works for that standpoint. And then we have concrete all along the banks of the Mississippi, most of it anyway. We have concrete revetment, and that's really interesting how they develop that. You can see we should not think of concrete as permanent, though. It breaks up and so forth, and it's a continuous job to upgrade that and to repair it here. Here we can see these dike fields right here, and you can see what they're doing is trapping sediment, and notice the size of these islands here, very much and scale dependent on the spacing of the dikes here. Here is a close-up of one here. But considering that, we have lost about 80% of our bottomland forest along the Mississippi floodplain. Here we have kind of a silver lining. We have new riparian habitat that's being created because of these dike fields trapping the bed material here. And so we do have some new habitat that might be interesting to utilize here. We got to decide what we're going to do with these. We'll look at them in more detail here shortly. In terms of our discharge and sediment regime here, it's easy. Most of the water comes out of the east, out of the Ohio basin, unless we get really bad IMSO events over here. And then we can get a flood coming out of Missouri. When that happens, we get a whole bunch of sediment. So the water comes from the east, the sediment comes from the west, and the Missouri system there, of course, that's, you know, they put in all these dams and so forth. So you can see that the current sediment load is much, much less than what it was historically. Not very much sediment coming out of the Ohio. In terms of the sediment here, this is a very important figure because it shows this decline in sediment in relationship to some of this structural engineering here. And you can see that, you know, initially we had back in the historic period, maybe 450, 400 or so million tons of suspended sediment per year. And then you put the dams in, and here we have closure of the lowermost dam on the Missouri River here in 1955, Alstad Reservoir, and just the sediment loads decline after that quite a bit. I've extended this out to about 2020. They think the suspended sediment loads have now kind of stabilized at about 85 or 90 million tons per year, but still that's a whole lot less than we used to have. I mentioned I put the revetments in here. So this is the cumulative distance of revetments. I showed you that concrete there. What's the importance of the revetment to the sediment load? If this was a class, what's that? Prevents erosion. And what does the erosion do to the river? It adds sediment to it. Exactly. Thank you. You'd get an A in my class. So historically, a big source of the suspended sediment was bank collapse. So they stopped the bank erosion processes. You reduce that sediment contribution there. And we got pretty good sediment budgets for the Mississippi. Also, the dikes you can see happening in there, trapping not the suspended sediment so much, but more of the bed load, the coarse sediment. That's the story of the suspended. That's an important figure. We'll come back to that one. Oh, my clicker is not attached. Here's one of my data sources I worked on a long time ago. These are the historic hydrographic surveys, beautiful, fantastic maps, large scale, and they record the channel bathymetry in great detail, all the way from Cairo, all the way down to the Delta, all the way to the head of passes, which is right where the Mississippi enters the Gulf of Mexico. If we zoom into that, we can scan these. I had to do this manually, not, something very different than what you guys are doing here in Edward's lab, of course. We didn't have some of those procedures developed then. So I got carpal tunnel syndrome, learned how to use the mouse in both hands and everything. But digitizing the channel banks, we can overlay those and look in great detail at the erosion rates in different places. Also, we can see the depth of the channel bed here. We can pluck out the deepest depth measurement, and that's the thalweg of the river channel. And we can compare the thalweg at different times then and look at how that is maybe incised or graded. And so we did that initially for 1880 and 1911, and then we did it, well, we just kept on going. It was so much fun using the more modern maps. But here we can see the rates of erosion or lateral migration of the river all the way from Cairo down to the Delta. And you can see the sharp demarcation between the alluvial valley where the river was free to erode around. The sediments were much less cohesive along the banks versus the Delta, where we have lower stream power and we have very cohesive channel banks that didn't allow that erosion to occur. Again, Red River Landing kind of serving as that border here. Our study area is right in here where we had some of the highest rates of erosion. I mean, sometimes these bends were 100 meters a year, right? That's a fantastic rate of erosion there. I would have loved to have observed that. Here's what I'm talking about with respect to some of these older cohesive controls on erosion. Of course, here we have Pleistocene deposits in contact with the active channel bed here. Some people are surprised when we tell them that the Mississippi River is not really a pure alluvial river. It's kind of set up as its textbook model as an alluvial river, but there's bedrock controls all up and down the Mississippi. Pleistocene, tertiary, all kinds of things going on there along the channel bed there that affect the adjustment of the river. And here we can see these Pleistocene, the prairie formation here, really prevent the river from eroding there, very cohesive. The more recent hydrographic surveys here, and much better detail, of course, much more high res and using modern methods there. So we do the same thing there, and we can overlay these. Here we see the channel thalweg from 1948 and 1999. And what I want to show you here is that, in 1948, the channel bed was about 3 meters or so higher than it is in 1999. So this, I think, is what we're looking at. This incision here is due to the reduction in the suspended sediment loads. One of the complications or the difficult things with working with big rivers that have been impacted by humans over long periods is trying to disentangle these different human impacts that overlap with one another. But here, because we're all the way up to Cairo, upstream of the nick point zone from the cutoffs, we can eliminate the cutoffs as being responsible for that incision there, and think that it must be due to the decline in suspended sediment loads there. And here we can see all the way from Cairo down to Red River Landing, looking at the cumulative change in the thalweg depth here. And you can see several very sharp changes here, but let me come back to the earlier one here. Here's 1935 to 48. And you can see the line is going up, so it's above zero. So we truly had in a grading channel at that time. And I've, of course, truncated the line right here because this is where we start to get the cutoffs, and you can't compare the cutoff part of the channel to the part that hasn't been cut off. So that wouldn't overlay properly. And also 1911 and 1935, this river was grading its channel bed at that point here. And then look, the bottom falls out. Here we have the nick points, also the reduction in sediment between 1948 and 1963. So it's incising, cutting down tremendously. And then it abruptly starts to reverse course here. The rate of incision decreases dramatically here. And so here we have 63 to 75, then we go up here 70. It's almost back to zero here. So we're almost back to kind of a steady state. I hesitate to use that term equilibrium. I've kind of gotten that scraped from my mind a few years ago. But anyway, I could update this figure for you, and it would show more aggradation actually occurring here over the last 20 years, especially down here around Red River Landing and Natchez. Okay. The thalweg is the deepest part of the riverbed. The deepest, and the reason why we use the thalweg is because it's we are not comparing apples to oranges, or as they say in the Netherlands, apples to pears. It's the hydraulically most significant part of the channel, usually where we have the highest velocity, the highest shear stress, and it's discrete. So we can compare one thalweg elevation to another thalweg elevation in the same point in space there. Yeah. Okay, what I wanted to note here again is that this abrupt change happening between 63 and 75, something's happening to the river then. When I got to Louisiana and started to work on the Mississippi, we thought that everything kind of been understood about the human impacts to it. But actually it was changing right under our nose. And what was happening is that all these islands were starting to develop on the river. And I say island here, I define that as a vegetated surface separated from the main channel bank there. So we have bars, of course, but sometimes these bars will persist unvegetated for decades and decades. And that's interesting because in this part of the world, as it is here, you know, as soon as you have any opportunity, vegetation will colonize that point, right? And so the same thing here. So these islands and these bars become vegetated and over time, and they start to evolve and take on a more complex characteristic. And we can go back and use some of these historic aerial photos again and historic maps and so forth to identify actually when they started to appear, presence or absence. And then actually in some cases when we have really good, which we do all up and down, these old black and white photos, we can actually measure the size and get the area of these bars, or excuse me, these islands, and look at how they've changed over time. So that's also a lot of fun to do and very interesting. And of course, work on your carpal tunnel syndrome a little bit and have these surfaces digitized and look at how they evolve over time here. And so we've done that, and we've got three time periods here. We've got an earlier one, 1965, when our data sources were not all consistent. The average date is 1965, I say, but some of the photos or some of the maps were older or younger or whatnot along here. And then we have one in 1995 and then in 2015. So a nice spacing in terms of the time sequence here of for comparative work. And you can see again, our x-axis is all the way from Cairo all the way down to 1,200 kilometers or so. Down towards the Gulf of Mexico. And this is the average size of these. And what you can see here is that, you know, this is an extreme example here, 2015, the same island, much larger than in 1995 and then in 1965. So the take-home message here is that they're getting larger. The vegetated surfaces are increasing in size in the river. If we look at the cumulative change there, we can see that you know, again, here's 1965. So we're getting this increase, especially in this reach here. We see the inflection here. So we're getting a strong increase in the size of the vegetated surfaces here. We look at 2015. So we've gone in about a 30-year, from 1965 to 2015, we've gone from just over 100 square kilometers to about just over 200 square kilometers of what was a river channel has now become land. And again, not a bar, but actually a vegetated surface there. So in summary here on this story, then you can see the number of islands, of course, increasing, the average area decreasing, but that's only because we have developed so many new islands. And when they start off, of course, they're quite small. And then the total area here going to about 200 square kilometers there. Other things that we can do with this is play with, we've got LiDAR, of course, great data set. And this LiDAR, of course, is a high resolution digital elevation model. And we've got it at 50 centimeter horizontal resolution. The vertical resolution is plus or minus about 20 centimeters. And, we can quantify these islands, their shape, the morphology. And that's kind of interesting to do, to compare the older ones with the younger ones here. And when we do that, if we look at, for example, a long profile of the island here, we can look at the slope of it. And we can see that here we have, the title's not showing up here. Here we have young islands here, and here we have old islands. And on the left side, these young islands have a much steeper slope than do the older islands, which over time, of course, are accreting. And you get extension downstream, and that's going to reduce the slope. Other processes become important in here. We get this sort of levee and chute morphology, very much due to the flooding coming in, scouring out, creating these troughs within the islands. But then you get a little bit of a levee formed around, a natural levee kind of formed around the edges of it. If we look at a tally then of some of the differences between the old and the new islands there, in general, the relief of the islands is greater in the old islands, so from 4.5 to 7.1 meters in height. The height difference between the islands and the floodplain, that's kind of interesting. We would think that the limitation to the height of these islands would be the floodplain surface there, but it's not. They actually can grow higher than the floodplain surface there. And then the downstream slope there, as I already mentioned there as well. And we can look at some of this, how these are showing up here. Here's one of these new islands here, taking a cross section with the LiDAR here. Here's our floodplain surface. You can see that it's the surface of the island is below it. And you can appreciate this would affect maybe the use of it by different types of animals, right? Depending on their sort of how well adapted they are to a wet or flooded environment. Some types of birds favor a certain flood regime or a certain vegetation regime that we would get associated with this. Here's an older island. You can see how much higher. In this case, the tip of this has become then above the floodplain surface there. These spikes here are obviously the levees along the edge of the river. This is what it looks like from a cross section there, then a new island there relative to that flood surface here. This is the official government flood surface here. You can see that, and then the old island here. And again, notice this sort of basin shape here. There was a study done about, I think it was 1997, Edward would know, on the Amazon by Mertz and Tom Dunn, where they looked at the development of these islands along the Amazon there. And along the Amazon is very nice because they have more space, the channel's wider there, and you get very distinctive levees along the edge of these islands there. So when we analyzed these, we were looking for something similar to what they found along the Amazon there. Didn't exactly find it, and I think that's because the Mississippi is a bit more dynamic and there's more shifting around and adjustment happening here. In terms of the vegetation itself, again, as I mentioned, it's developing, it's evolving, becoming more complex a little bit, just simply using NDVI here. And we can see between 1996 and 2014, between Vicksburg and Natchez, that the vegetation is becoming denser on these islands here, going from, it's cutting off here. So this would be water, sand, scrub soil, would be the red here, and then moderate vegetation is this blue, and you can especially see the difference between the blue and the green here. So going from moderate vegetation to denser vegetation later on in time. You again using the LiDAR here, extracting this. This is really interesting here. Using the polygons that we digitized in and extracting these islands here. They look like a bar, but that's just because it's the raw LiDAR digital elevation model here. Here is the bar extending out from it. My plan was to go back and to get the bars too. Haven't done that yet. I need some students there to work on that. But anyway, here we can finally come up with a number for you about how much sediment is being stored in these islands here. And so the way we do it simply is we've got this vegetated surface then, and so the total amount of sediment in a bar would be that which is contained within the bounds of the vegetation and extending down to the average low water surface there. That's our Z value there, and so each bar has a different Z value there. And if we look at that, you know, what's a number? Sometimes these numbers, you know, it's hard to get a sense of what it really means here. So almost 1.2 billion or 1.8 billion cubic meters of sediment, mainly that's coarse sediment being stored in these vegetated islands here along the Mississippi. And put it in a little bit of a human perspective here. I tried to make this more local by looking up the dimensions of your local football stadium here, but all I could find is that it now houses 55,000, I think. So that's a little bit smaller than the Superdome here in New Orleans, which houses about 75,000. But the difference is that the Superdome, Wikipedia gave me the actual volume of the dome there, whereas I couldn't find that for Singapore. What was the total volume there? So 337 times you could fill up the Superdome, this big stadium, indoor stadium, 337 times with this much sediment there. So, you know, if this was the Netherlands, we'd be thinking, we can use that sediment, you know, we can go out and we're going to move it around, and they have every grain size quantified basically. But we haven't started to even think about, you know, this as a natural resource, and could we use it in another context there? Because these aren't natural islands, right? That's the point there. They're pseudo-natural, I think. Should we keep them? Should we, you know, what are the different environmental protection that we should manage these by? This has not even been thought about, that I can tell thus far, with the Army Corps of Engineers, which is responsible for that. However, there is a paradigm change that is occurring, not one that occurred as abruptly with a flood event, but there is a change of mindset that's occurring. And that is the U.S. Army Corps of Engineers is thinking much more now about connectivity. That, you know, before, when I showed you the first two photos, the idea was to disconnect the river from its floodplain. We're going to disconnect it. And that's kind of the, you know, the paradigm, especially in Western Europe and in North America. Well, now we realize that was a big mistake, and we're trying to reconnect the surfaces in certain places if we think it's okay, right? Depending on societal values, and, you know, you might have some things along the floodplain like cultural heritage and so forth, or endangered species and so forth that can limit that, but we are starting to come at this much more explicitly then. So that's a good thing to see that happening in the last decade or so along the lower Mississippi, because it's been such a degraded riparian corridor for so long. And two key ways that they're doing that is to reconnect oxbows and floodplain water bodies to the channel. They go in there and they dig notches and so forth, and then that's funded some of our research actually that I'll show you. And the other one is to dig notches in these dikes that we were talking about earlier here. And they realize, hey, these dikes are preventing the flushing out of these side channels, and these side channels are becoming infilled with sediment, and that's not a good thing for biodiversity, aquatic biodiversity there. So what they're doing now is putting notches. They've put hundreds of notches in the in these dikes here and are allowing water to flow through there at a low flow duration. So, you know, it doesn't take a big event now to flush these out. Now you get all kinds of, you know, high and, you know, fast and slow moving water, and that's good for species diversity there. And it's, you know, the biologists that are kind of monitoring these sites are finding that the success is very high when they do go in and create these notches there. So I haven't heard them apologizing yet for doing this or anything, but it's good that they are moving in the right direction. And the other thing was reconnecting floodplain water bodies in the interest of different types of riparian habitat, fish, to increase fish linkages between the water bodies and the channel back and forth. And to do that, to kind of move in that direction anyway, we're doing some overbank sedimentation research. And the Nature Conservancy and the U.S. Army Corps of Engineers is interested in how long it's going to take these water bodies to infill with sediment. So this was a good link to do some good geomorphology, in my view. And we got into this incidentally, actually, and it was a big flood that sort of triggered it, and especially this big flood of 2011, which is the highest flood along the entire Mississippi. Not quite the biggest one, just a little bit shy of the 1927 one in terms of discharge, but in terms of flood height, it's by far the highest. It's the highest along the entire valley there. And so we went in and did some sedimentation work there, and then we also came back and set up some stations there and monitored it in this flood, and also in 2020. And the 1973 one I show there because we're going to do some comparison there, came about because of my PhD supervisor working on that. And one of the reasons why I started to work in this particular area to do flood sedimentation work is because, you know, when you're doing this kind of work, you need to go to the floodplain, put in a sediment trap or something like that, come back after the flood, look at your sediment and so forth. And, you know, you want to flood. You want it to flood. You don't want anybody to get hurt or anything like that, but, you know, you want to get some data, certainly. You don't want to wait 5 or 10 years for that to happen there. So this area, convenient for just a lot of different reasons, was a perfect place for us to work here at Natchez, kind of just downstream of that in Red River Landing. And my PhD supervisor had already worked there on the 73 flood event there. And you can see one of the issues here is that there's no doubt about it. So we have an increase in these are the annual high and low stages along the Mississippi here at Natchez, and you can see this increase. However, you can see the impact of the cutoffs here. So we had some decrease, and then it stabilized there, and then boom, right about there when we put the dikes in, we start to see the increase in the flood heights again. So there's a pretty clear demarcation at this time period here. If we look at the low flows, of course, it's not a flood, but it's a good indication of the surface of the channel bed. Yeah. So the low flows here, I think, give us a better indication of the aggradation that's occurring down here along the channel bed here. This is a 1973 flood event. Here is the 2011. I promised you that's the highest one ever. And then we have the 2018, 19 and 2020 event right in here. And one of the things that's happened is that they built this flood diversion structure back in 1931 to prevent New Orleans from flooding. Hardly ever used it. About every 10 years from 1931 to about 2000, 2005, whatever, about every 10 years, you know, they have to open it up. Now it's every 3 or 4 years, sometimes twice in 1 year, they have to open it up. So all of a sudden, this structure is, you know, they're getting their money's worth out of it. This is what it looks like. It's like 2.3 kilometers long, and it's controlled by removing, I don't know, something like 3,000 pins that are creosote-coated wood. You can see one of them right here. They pull that out, allows the water to flow out of there. And here we can see number of days open and light gray and the maximum discharge. I like to remind my Dutch colleagues that this is more than the average discharge of the entire Rhine River. So 3,400, coming out of this flood diversion structure right here. And now it's pretty regularly used. Here we're looking at not the height of the flood, but actually the length of the flood or the duration of the flood, the number of days of flooding there, because it's not, in terms of being a problem, it's not always how high it is, but it's actually how persistent the flood is. And you can see here from 1940 to 2022 here, something changed right in here. We had a number of years where we had no flood at all, no flood, no flood, no flood. And then boom, about 1970, we start to get all of this higher amount of flooding. And we get these really outliers right here, 2019, where it was over 200 days, the water was overbank that long. Combination of these two events, 286 days of flooding. So it was a whopper. This nice pair of legs here goes to my my PhD supervisor, Professor Kessel at LSU, and he published kind of a landmark paper from this 1973 event in geology, looking at the overbank sedimentation there. And so when the 2011 event happened, guess whose door I was knocking on? Like, hey, Dr. Kessel, come on, let's go back to the field. And we'd been back here a number of times when I was at LSU. Let's go back there and revisit these old field sites of yours. And as best as we could, we did. You can see how high these people were prepared for the flood. So they thought these are kind of weekend homes, something like that. Some of them can actually get very plush and very nice, but just completely blasted out in 2011. These are the field sites for that 1973 study here, Old River Control Structure, just a little bit upstream and then downstream of that. And then here's where we did in 2018-19 and 2020, a bit upstream parts of it, but also overlapping directly with some of it. Here it is in 2019. They had just repainted this church in 2011. This is a field site I've been to a number of times. And, they're just having to abandon this small settlement now because they get pelted by floods so often now. And I remember we used to go look at the flood line from the 73 event back in the 90s. So it was on you could see it for some 20 years, 25 years or so along there. So completely abandoned there. One of the reasons why, again, coming back to the geomorphic complexity, I wanted to work on this area is that you have a full range of depositional environments. That's pretty cool. That are, not protected by a levee. So they're getting inundated every year. And so we can see how the sedimentation varies across these different depositional environments there. And of course, the fisheries and the biologists are interested again in how the sedimentation affects the habitat, because at flood stage, certain fish move in here and do their magic, spend a little bit of time there, and then come back out and move up and down the river corridor there. So it's a really important riparian habitat for some of these fish. This guy in particular that I love, the alligator gar, which can get several, a couple meters long. There's still a lot of big ones there. Here you can see the flood line on the tree and so forth. We've also done a bunch of coring. I'm not going to present that data to you. We've got 5 minutes. Okay, wrapping it up here, Edward. Thank you. We've got pressure transducers in there looking at that. I'm not going to present that to you here. Here's the floods that we went back and looked at that. And we put in 2017 these sedimentation maps with the idea that we'd come back the year later and get the sediment. Well, we didn't expect that we couldn't even access the site because it was underwater for so long. So we couldn't even get back in there in autumn of 2018 until 2019. And let me tell you, that was some jubilation when you actually find these things and dig around. We got about half of them back, actually. Other ones we had the GPS point and so forth, and we had tape and so forth. We could find out where we'd been here. Here is what some of this looks like here, identifying the flood sediments from the older buried surface there. Very clear, easy to demarcate there. And we get very good measurements. Some of the other types of sedimentary bed forms here, really nice from a crevasse splay that happened there. Massive amount of sediment, big sand sheet here, the flood line up in the trees. One of the things is you got to know your study site, and again, know the history of it here. This is old back swamp. And back swamp usually as a depositional environment gets about 2 millimeters per year. That's the sort of benchmark number people will tell you. 2 millimeters per year for back swamp in terms of sedimentation. We're getting 10 millimeters back in here. The tree roots are all buried. So it's happening very fast. Why is that? Well, because they had these cutoffs. And here we can see the back swamp in this clay. This is a mid-Holocene in age here. And you can see this gray clay, and then it's overtopped with the more recent natural levee sediments there. So a complete, clear demarcation between these sedimentary environments here. This should be back swamp here. You can see the old in situ cypress stumps there as well. So the depositional environment is actually changing there because of the management, because of the cutoffs that's changed the sediment regime there. If we look at some of the suspended data and some of the discharge data for the 18 and 19 and 20 here are our nice little peaks there. This is about the flood stage here. You can see we're kind of getting this sort of exhaustion of sediment there. I mean, usually these systems kind of reload their sediment supply. But in this case here, it just looks like by 2020, we're just kind of losing some of that sediment here. Other thing I point out here is that mainly our sediment loads coincide pretty close to the discharge peak, or at least during the flood event itself, we have peak sediment. That means the sediment has an opportunity to make it overbank. In 2011, what happened is that the sediment peaked. We have pronounced hysteresis, so the sediment always peaks, a month or so before the discharge, but the sediment peaked so far in advance that it didn't have a chance to even make it onto the floodplain. So actually, from this 2011 event, high magnitude, it went up and down so quick, it didn't leave much sediment. And that's interesting. So we think of the geologic, long-term rock record importance of these big events should be recorded by sediment. But this one is not, the 2011 is not really leaving much of a geologic signature at all. And here we go with the average sedimentation here in 1973, a whole lot more sediment there. Hey, Dr. Kessel, what's going on there? And a whole lot less of it here, average, but still pretty good. And here's our unit rate of sedimentation, millimeters per day here. This 2018 thing was so long, 286 days combined over bank there. We just had a lot more sedimentation. A couple more minutes, Edward. Okay. Here we have, looking at sedimentation here, the story is in 2020, generally less than in the 2018-19, 2011, much less than what we had in 1973. And that's for a range of depositional environments there. Looking at this figure again, I think one of the differences between 73 event and now is that we're further down that track. There's less sediment in the pipe now than what we used to have back in 73. I think that's one of the things to consider there. And then grain size there, maybe a little bit more sand here in the recent ones because that 2018-19 was so long that it allowed just a lot of that clay to be deposited in that slack water sedimentation there. Whereas in 2011, high energy, high velocity movement there and moved more sand into these environments there. I won't go into all of this too much here, but I'll just point out Dr. Heitmiller here went out at the peak of this 2019 event and took velocity measurements back in the floodplain here in different places. And what he found is that, you got about 0.3 or 0.4 meters per second, but that the flow direction actually is interesting. The flow direction was, not lateral like the textbook models show you. It's all down valley, pretty much parallel to the main channel there. So when you get these big events and you get further away from the bank, you drown out that sort of lateral influence that the textbook model sort of show you. And here you can see the flood height across the depositional environments, 3 to 5, 6 meters here. So this was a big event happening in 2019. We can, in some ways, you know, we were wondering, hey, what happens if we go out to the exact same point in space in 2020 and look at the sedimentation? Not bad for a real world. Not a laboratory flume here, except that it's about half the sediment, you know, but not bad there. So you can see in 2020. So just didn't have the duration in 2020 that we had in 1819. So much less sediment there to go with. So I want to make sure I acknowledge my collaborators, Heitmiller, my former PhD student at Austin, some of his grad students as well, Nature Conservancy, property owners along the river, so important to get access to these sites here. Army Corps of Engineers, U.S. Fish and Wildlife Service, they just put us up in a big house on this site here. It's fantastic. So that's been a great collaboration there. And in Dutch, this is thank you, of course.